What I'm going to do is a 30-minute program for you all about dry ice. Now, you notice I'm putting these gloves on. Dry ice is really cold. Let me show you just an example of how cold this stuff is. It is cold enough to create a fog coming off of it. I'll stand off to the side so you see a little bit of fog falling down. Um, it gets even more vivid when I blow on it. You can see that. This stuff is negative 109 degrees Fahrenheit, extremely cold. What we're going to do throughout this program is learn what this stuff is and how it behaves in different scenarios. So, the first one is it's just sitting in the room. And as we can see, something's happening. When you see a fog coming off of something, or if you see bubbles or gas, that usually means there's some sort of change happening. So we're going to explore what kind of change we can see with this dry ice. So you're going to get a close up look and you're going to see that it's white. And this is actually kind of like a snow that gets packed in together. Now, here in the room, you can see a little bit of fog coming off of it, but we're going to heat this thing up using some water. The first way I want to do that is I'm going to get some small pieces and we're going to place it in this tray of water right here. So let me swap this large piece out for some smaller pieces, and we're going to get to enjoy the way this looks momentarily. Here we go. Don't need this big piece, but I do want some smaller pieces. There we go. Now we're starting to see some cool fog. So all that fog coming off of our dry ice, that is the same stuff as the dry ice. It's called carbon dioxide. Now, you may have heard that word carbon dioxide before. I want everybody to take a big, deep breath of air in and let it out. That stinky breath that just left my mouth is carbon dioxide. So our bodies use oxygen. Now, the gas coming off of this right here is CO2. So this is the same stuff that we breathe out. Now, ours doesn't have this fog on it normally, but it does in the winter, right? Well, that's because this dry ice is turning into a gas and this water is warming it up. And here in a moment, you're going to see these things. Oh, it's already floating. So this piece of dry ice is, you can see that gas coming off of it. You can see these little tiny jets coming out the side of our dry ice. Here, I'm going to kind of break this big raft up into little pieces so you can see these little tiny pieces floating around. Oh, this one's spinning. I love it when they spin on their own. So it's propelling itself. So it's its own little boat. Like, so this little piece of dry ice is floating, and then the gas coming off of it propels it, and it's spinning it in a rotation. I think it looks so beautiful when it is rotating and moving around and floating, and you can see that fog coming off of it. So carbon dioxide, let's talk about that for just a moment. Carbon dioxide is all around us. So it's a gas that is all around us, and plants are going to be using this carbon dioxide, and it's very, very, very common. So why does dry ice seem so different? I think that's a really good question. So dry ice is carbon dioxide, but in the solid form. So we're talking about, we breathe out the gas. Well, the dry ice is in the solid phase. So it's still the same stuff. That's kind of the weird thing. The dry ice, even when it is white and looks very different than the air we breathe, it is actually a solid. So here's what we're going to do. We're going to get this big piece again, and I'm going to show you another way we can explore it. It's going to be with a large pan over here. So this large pan is made out of metal and it is room temperature. So we're going to take this solid dry ice and we're going to touch it to this metal pan. Now, this is very cold. In fact, a lot colder than this one. It's almost 200 degrees colder, really. And we're going to touch it together, and this is going to transfer heat to our dry ice. Are you all ready? I think it's going to be pretty fun. Check it out. Woo! That's the lovely sound of science. Should we hear it again? You might be saying no. It's a pretty brutal sound. Let's take a listen. Whew. All right. That is from a vibration. So think about it this way. We have this metal pan, and it is, well, it can reverberate. It can shake and create a sound wave. The reason we're hearing a sound wave is because this dry ice is going from a solid, and when I touch it, it turns to a gas because it's warming up. That process is called sublimation. We're going to explain that as this whole program goes on. When it turns into the gas, that gas pushes against the metal, and then I push it back. And then it turns into more gas and pushes it away. And then I push it back. And it goes back and forth on a small scale. You can see it doesn't really move a whole lot, but on the low level, it moves quite a bit. And it creates that sound wave that we can hear. So that's just one other way that we can explore dry ice and explore this phenomenon called sublimation. I want to take a little bit of time and explain what that is. But first, I need to clean up my space just a little bit. So I'm going to set a couple things over here. So sublimation, let's talk about that. It is a phase change. So when we talk about phase changes, we talk about solids, liquids, like I just poured down, and gases. Now there's also plasma, but we're not really going to go into that today. So solids, liquids, and gases. Well, we are familiar with solids, like the ground we're standing on and the table right here. We've seen liquids like water, milk, all that kind of stuff. And then gases we breathe. Now, normally we kind of forget about gas because it's usually invisible. The air between me and the camera is invisible. That's why you can see me standing here. But it's also a state of matter. So solids are very obvious because when they smack us in the face, it hurts. And liquids, well, we're always familiar with that, like when we take a shower or wash our hands. But those gases tend to get forgotten. So when we talk about phase changes, that's when an element or a compound will go from one of those phases to another. And let's visualize that. So when water goes from a liquid to a solid, I think we know that one, freezing, right? When it goes from a solid to a liquid, that's melting. Does anybody remember liquid to a gas? Evaporation, right? Or boiling. So if you have a pot of water and heat it up, it'll turn to a gas. It'll turn into that steam. And then if it goes from a gas to a liquid, that's condensation. Now, this dry ice skips one of those phases. So let's think about which phase it might be skipping. If we have a solid and we see it going to well, that's not really going to a liquid now, is it? If it's going from a solid to a gas, that's that sublimation that I mentioned earlier. So sublimation is when you go from a solid directly to a gas and you skip that middle liquid phase. I want to show you that. So I have some hot water and a graduated cylinder. Now, a graduated cylinder is simply a container that is tall. So if we get this right here, we're going to, actually, I'm going to scoot this out of the way just for the time being. We'll come back to that momentarily. And we're going to get some dry ice and put it in. So we have really cold dry ice. This stuff is negative 109 degrees Fahrenheit. So negative 109 degrees Fahrenheit going into, oh, I missed, nearly boiling hot water. I wonder what might happen. Take a look. That is a lot of sublimation. Now, we're going to look down at the very bottom, and you're going to see the small pieces of dry ice. So if you look closely, you'll see those white pieces kind of moving around and jostling back and forth. And then what's right next to those pieces? Bubbles. You get to see these gas bubbles coming up. So that dry ice is going from the solid phase into the gas phase. So you see these bubbles, that's the gas. That's carbon dioxide gas. That's the same stuff as my stinky breath. Now, it looks different because it's going through that phase change and you get to see this really cool fog. But if I cover up the top of this, check this out. You can see all of that gas coming out right here. So this fog is all coming from that dry ice. That's a lot of gas, right? Look at all of this gas. This is so much. You can even kind of pressurize it and it shoots out like a steam engine. That's a lot of gas. And what we're going to do is we're going to trap that gas so you get to see just how much is coming off. Here we go. Ooh, this is one of my favorites. So we're going to add a couple more pieces of dry ice. Let's get our tongs to grab these. Now, I don't want to touch dry ice with my bare hands because of how cold it is. So I'm using tongs and I'm using gloves. Next up, I've got some bubble juice. Let's add our bubble juice to our concoction. Are we ready? What do we think is going to happen? Here we go. Oh, isn't that cool? I like to call this the bubble brain experiment because it's a bunch of bubbles that kind of look like brains oozing out of the top. Now, the reason we see these bubbles is because the dry ice is turning into a gas and our bubble juice is trapping all of those bubbles that are coming off of the dry ice. And those bubbles are being forced up because more gas keeps coming up and up and up and forcing it out of the top. And then it goes over the edge and down. Now, if we look closely, what I'm going to do is I'm going to pop some of these bubbles and you can see some of the fog come off of it. How cool is that? Oh, got some really good bubble juice today. Doesn't really want to pop. Doesn't want to come off of my hands either. So we're learning about dry ice. And this is one of the classic experiments that you'll see during our Halloween period in the fall. So this is really fun. You do have to be careful when using dry ice because of how cold it is. And you also want to be able to let that gas come up and out. For our next experiment, instead of creating thousands of bubbles, I want to create one bubble at a time. And this is one of my absolute favorite demonstrations out of everything we do here at the Museum of Discovery. So I'm going to set this off to the side and get our next experiment ready. I love this one because it combines a couple things together and it just looks super cool. So we're going to put some dry ice in this. It's called an Erlenmeyer flask, and it has a hose attached to it. And we've got some bubble juice in this container right here. So let's see if we can snag a couple pieces of dry ice that'll fit in there. Oh, there it goes. Let's get a couple more. I'm going to want about 4 medium-sized pieces, but I've got some smaller ones here. That'll be good. I did spill a little bit of dry ice on here, so I'm going to wipe that down just momentarily because I want a really good environment for our bubble that we're going to create. Now, I'm going to put a stopper in the top. Check this out. All the fog is coming out of this hose and funnel. Now, that's going to be important for this next portion. Take a look right here. So I've got some bubble juice, and we are going to create a dry ice bubble dropper. How cool is that? Here it goes. Oh, that's awesome. I love it. We've got another one coming to join it. Boom. Oh, let's see if I can attach and reinflate one of them. There we go. Now we're starting to reinflate our bubbles, making them grow and grow and grow. I'm going to take that one away. Well, it kind of looks like Mickey Mouse from the top. So these bubbles right here, if you notice, they really only want to go down. For this, ooh, we got a bouncing bubble. I love it. I'm going to try and toss this one up into the air and watch which direction it wants to go. Even when I try and go up, it falls down. That gets into the idea of density. So dry ice turns into it's carbon dioxide, and when it turns into the gas, that gas is a dense gas. So it wants to go down. When we talk about density, think about if you were to have a rock and you put it in water. Well, that rock's going to sink. That has to do with buoyancy, but also density as well. So that's why our water stays in the bottom of our glass. If we're in space where there's no gravity, it would just kind of float everywhere. So this dense gas goes down. So it sinks down. And I'm going to show you, we're going to do some bubble Olympics here. I'm going to show you that this bubble, it can dance. It can do the hula. And it can also get really excited and jump. It can look at that. Oh, he's kind of wobbly today. But I love looking at the way these bubbles behave. Oh, there we go. He's wanting to jump away. And then I'm going to release over here and it'll fall down to the table and then pop. So this will be our last bubble on our bubble dropper to watch. I'll see if I can drop this one to see if it'll, I'm going to wipe down the table to see if we can get one last bouncing bubble. Bouncing bubbles are my absolute favorite. They're really hard to get. You have to have just the perfect surface. Sometimes you get them, sometimes you don't. And when you do, it just makes your day that much better. Let's take a look. Oh, we got a bubble sticker. That's okay. Those are really cool too. So let's say goodbye to our bubble dropper because I'm going to try and attempt one of the most difficult demonstrations at the Museum of Discovery. It's going to be called the ghost bubble. So we're going to try and make one single large bubble using this bowl right here. So this is a bowl that has a little bit of water in the bottom. And what I'm going to do is I'm going to dip my finger in here and add a layer of bubble juice to the top of this container. Now, normally you don't want to touch your finger near anywhere a bubble is going to be because it will cause it to pop. But for this demonstration, when you add just a little bit of bubble juice to the top, next up, we're going to add a medium-sized piece of dry ice into our container. Let's see if we can find one. Here's a perfect one right here. So I'm going to add this piece down inside, and it's going to start sublimating. Now, my next task is to find my pink string that I had that I don't know where I put. Where did I put it? Oh, it's got caught. I got caught in my towel. So we're going to get this pink string, and we're going to stretch some bubble juice across this lid. Now, this one's really hard to do. The reason it's so hard is that bubble may want to pop. So I have to go very slowly and kind of zigzag back and forth. I can see I've got my lid. So let's see if I can. Oh, it popped just at the last moment. I'm also seeing I need to use a little bit hotter water with a little bit more dry ice. So I'm going to add just a touch more in there with a little bit more dry ice. Let's use another large piece from over here. All right, this should be a little bit better. Anytime you're doing an experiment, sometimes you need to change some of your variables. A variable is something that can be different from one experiment to the next. All right, let's see if we can get this one to go. So I can see I've got the bubble on the side closer to the camera, but it becomes very difficult to close this one off. Oh, we got bubbles underneath. Oh, no. Let's see if our main bubble will grow. We got a big one over here. And if I remember right, got a second container, so I can try this again. While that one grows, I'm going to prepare a second one for you. Ooh, how cool is that looking? We're going to try this one more time. Normally, you only have 1 or 2 tries to be able to get it right. But we're going to try it today. We're going to see if we can get this one for you all. All right, I'm adding my bubble juice to the lid. Now we need to add our bubble lid and see if we can get one big bubble rather than lots of small bubbles. So nice and slow across the top. Oh, it popped on me again. The last little bit is the hardest one. All right, we're going to try one more. And if we don't get it on this, if we don't get it on this one, we may just move on to the finale because that one's a lot of fun. But I do like seeing a nice big ghost bubble. I think we've got it. Got it. Got it. Third time's a charm. So as that grows, you get to see that single bubble growing up. You might even see some reflections. You might even see how it is. You'll see some rainbows on the top of it. It looks so cool. I love this demonstration. The rainbow, the smoothness of the bubble, it's just beautiful to me. And to know that it's only being filled up with carbon dioxide. So we don't have a pump creating more air. We're not waving the bubble through the air or anything like that. Whoa! Looks like some of our bubble juice dripped down to the bottom. Check this out. We got some side bubbles going on over here. I wonder if I can pop those. Get out of here. Go, go, get out of here. Be gone. Well, that actually kind of worked. Interesting. So we have this one large bubble. Oh, we got more side bubbles coming in. Get out of here. No, go away. All right, we're getting taken over with the bubble brains like before. So as that bubble juice leaks down the sides of the bowl and gets in the water, it's going to then start creating lots of bubbles underneath. I think it's about time for our final set of demonstrations. So we've been exploring dry ice. We've been learning about how this solid turns into a gas. And for our finale, we're going to show you a different type of container. I'm going to start with this one right here. So the main difference in this container is that it is going to have a lid. Now, in all of our other demonstrations, we haven't had a lid so far. That's because that gas takes up way more space than it does as a solid. So if we try and put a lid on it, I wonder what might happen. So we have hot water right here. We're going to add into the bottom. And as you can see, this is just an old coffee container. So we're going to fill this up with a little bit of dry ice. And we're going to see how that coffee container lid is going to behave when we add our dry ice inside. So just like before, we add our dry ice. Boy, I'm really good at spilling dry ice today. When we add our dry ice, you're going to see that fog like we've been seeing this entire time. We might want just a little bit more fog than that. So we're going to add even more dry ice, maybe a little bit more water too. There we go. Now we're getting some fog. Because we want a certain amount of fog, because when I place this lid on, that air is going to kind of push. Oh, let me see if I can get this on here. It's going to push a little bit against the lid. Whoa! Every once in a while, it'll pop off like that. Wow, that was cool. I think we might need to try that again. So we're going to place the lid on. I'm going to, there it goes. And it builds up that pressure and then pops right off. Now, I'm going to try it with a smaller coffee container. So we're going to transfer all of our ingredients from over here to over here. Now, with a smaller container, I wonder, how is it going to behave? Is it going to pop off slower or faster? Is it going to pop off quieter or louder? Or is it not going to pop the lid off at all? What's your hypothesis? Now, a hypothesis is a guess that you have. Oh, that's kind of neat in and of itself. Look, that shows how the heavy, dense gas is going to want to go down. We were seeing that with our bubbles earlier, but we really get to see that with some of our fog right there. We can even kind of pour it into this cup. That's neat. So let's pour our ingredients in here. Oh, there's our dry ice. Okay. So we have it here now. And we're going to put our smaller lid on. Are you all ready? Let's see. Might be taking a, whoa. That was pretty fun. I'm gonna have to move over here to get it because it went a good ways away. Thank you, Sean. So it popped louder. That's because this lid stays on just a little bit tighter. So when we have a tighter lid, it makes more pressure inside. So it's pushing against all sides on the bottom and on the walls. And then it flips that lid up. Wow, it landed in the exact same spot again. That's neat. So we are dealing with pressure at this point. Now, what we don't want to do is we don't want to put dry ice in a sealed container that can be really strong. What we're really going to want to do is we're going to want to put a dry ice in a container that can ventilate. So for example, our cooler, this cooler ventilates along the sides. So the dry ice doesn't build up too much pressure and cause the whole thing to explode. That would be really dangerous. So whenever we're putting it in a container that has a lid, well, that can spell bad news. You can see the lid starting to push up at the top. And then at a certain point, that lid is going to fail right on cue. Now, there's one final type of container that I want to show you. Now, this is a special container. It's an ancient artifact known as a film canister. Now, this film canister is something a lot of people are not aware of today. You know, back before digital cameras, we had actual what we called a photographic film. It would do a chemical reaction based on light hitting it, and it would create a negative that would then be developed at a camera store. Look up the history of Kodak when you have a few moments. So this lid snaps on really tightly, but it's not one of the screw-on lids. A screw-on lid would be too much pressure. So this is still a lid that snaps in place. So what we're going to do is we're going to place our ingredients of the day. We're going to place some dry ice. We're going to place some hot water. Now, to measure it out first, I'm going to show you, we're going to do about half full on this one, maybe a little bit less. That'll work. And I've got a second one over here that we're going to use. We're going to create a film canister rocket. Now, I'm going to actually flip these over once I put the lid on. You'll see why here in a moment. And what we're going to try and do is we're going to try and do what's called a split screen for you all. Kelsey's going to set the camera right here, and we're going to look right at these. We're going to aim that camera down. You'll be able to see them. Let's see. I've got a piece right there. Sean's going to be pulling up our split screen momentarily. It takes a team to put on these shows, by the way. So much thanks to the crew, our studio. Let's see. I'm going to need to break that one in half. Oh, broke it in too many halves. All right, I think we're about ready. Sean, how are we looking on the split? Oh, that's looking good, Mr. Carlock. That's nice right there. So we can see our dry ice bubbling away. And all I need to do is place these lids on there, and then they are going to build up pressure and launch. Are we ready? This is our final experiment, so I wonder what it's going to look like. Hopefully, it'll be pretty cool. So I have to be kind of careful when I put these on here. All right, snap for one. Oh, can't get the other one. It doesn't want to go. Let me reseat it. See that other one, though? Boy, it launched in no time. There it is. Now we're building up some pressure. This one's going to be fun. I might even plug my ears for this one. Whoa! Look at the aftermath. Look at that right there. That is that's pretty awesome. That's a lot of power for a little tiny film canister. So we see the blast radius where it shot all of the gas and all of the water out. And so you had you have Newton's third law. So for every action, there's an equal and opposite reaction. So when the gas in the liquid went down, the rocket, the container, went up. And it looked really, really neat. So what we're going to do is, if I can scavenge and find them, we're going to do that one last time for you all, and then get your questions. So let's see. I've got one piece of dry. Oh, thank you, Sean. We're going to get this one more time. It's just like too much fun to not do again. Just too much fun. I hope you guys don't mind. All right, we're going to add a little bit of water just like we did before. Do we have both lids? I see one lid. I don't see the other lid. We might only be able to do one. I think it might have fallen off. We'll take a look. We'll see if we can find it briefly. It's usually under the table. Oh, yep, found it. Got it. All right. I think I have it just about ready. As you can tell, I really enjoy this program. So let's see if we can get our canisters ready. I'm going to do them one at a time. This one was really hard to put on last time. So we're going to go 1, 2, step back. Whoa, there's one. Oh, there's the other one. Woo! Now that is some fun. So we've taken 30 minutes to explore dry ice, the carbon dioxide solid that sublimates into a gas. That gas looks really cool, and we can learn all about it by heating it up with water and trying it in different environments. And the last thing you want to remember is that you don't want to pressurize that dry ice, because it can basically cause a container to blow up, which can be really dangerous. So know that we've gone through safety training to be able to do these shows safely for you all. So I hope you enjoyed it. We're going to turn it over so that you can unmute your mics and ask any questions you have, or just simply tell us what was your favorite part.
All right. How about a big round of applause for Mr. Thomas? Woo-hoo-hoo-hoo. And for sublimation. It's kind of a mouthful, isn't it? Sublimation. Changing from one state to another and skipping the one in the middle. Fascinating. So if you guys have any questions, we would love to answer those for you. If you want to go ahead and unmute your microphone, ask your question, and we will answer it to the best of our ability.
And because one question is, why does some of the bubbles go up and then the other ones went down?
Why do some bubbles go up and some go down?
Yeah, some of them
graduated. So in this one, the reason these bubbles came out of the container was they were being forced out by more bubbles being formed at the bottom. So think about it like really like a water hose. So water hose, it pushes the water that's at the beginning of the hose all the way to the end, because more water is coming through, and it just keeps pushing it through. So these bubbles were being pushed up because more bubbles were being formed at the bottom. So it was a conveyor belt of pushing more and more and more bubbles. But you notice once it got to this top part, it turned over and then started going down. Most of these bubbles are going to want to go down because they're filled with that heavier gas, carbon dioxide. So CO2 is going to sink down a little bit in our atmosphere compared to just like the nitrogen and oxygen that's floating around us when it's concentrated. Normally, carbon dioxide just kind of floats around, but when it's concentrated, it will sink a little bit. So if that answers your question, let me know. But if you want a different perspective, you can rephrase your question.
No, that's cool. The next question is, how do you make dry ice?
Dry ice, we actually use an industrial supplier to provide our dry ice. The company basically decompresses, they pressurize and then decompress carbon dioxide gas, and they turn it into a liquid, and then they release that into like a snow in a really cold room, and then they pack that snow into a powder, which is like what we have when we pick it up. We actually get it from the grocery store, but you do have to be 18 years old to purchase dry ice because of how hazardous it can be with touching or with building up pressure. That's a great question.
Okay, thank you. Another one is, how long does it take to freeze your skin if you touch dry ice?
That's a great question. So if you were to get a large piece that's in our cooler, and if you were to pick it up with your bare hand and hold it tightly, it would just take a few seconds for it to start damaging your skin. It is so cold that it would, negative 109 degrees Fahrenheit is really cold. When we think about how cold it was the other day, in mid-February, I think it was about 0 degrees. So that's 0 degrees Fahrenheit. This is still 100 degrees colder than that. So think about the temperature difference of the coldest day of Arkansas, which was 0 degrees, and the hottest day of Arkansas, where it's like 110, like freezing cold to like sweating like super hot. So if we go that temperature difference, that's how much colder it is from 0 degrees to negative 109 degrees. So that's a big temperature swing, and it's so cold that it would just take a few seconds for it to start damaging your skin. It would freeze your skin, freeze your blood, freeze your muscle, and it'd give you something called frostbite, where when that tissue thaws out, it's dead. So that's not something we want to experience.
I'm curious to wonder, if you compare the hot to cold, if you touched a 109-degree metal pan that had been sitting on the stove, how quickly would that burn you? I wonder if those times would compare to one another from really cold to really hot, if they would burn your skin at the same rate.
Well, and if you think about it that way, that would be an unfair
Okay.
test, because negative 109 is like 180 degrees colder than the room temperature. So we would have to go 180 degrees hotter than room temperature. So you're talking, 200
really
something
hot.
degrees, which that would burn you really quickly.
Oh, any other
Okay,
questions?
thank you. I have one last question, and it is what do you think would happen if you had a balloon with hot water in it and you put a little piece of dry ice in it? Oh, and
Oh, fantastic question.
and you tied the balloon
I think
up
we might
really.
actually. Yeah, that's super awesome. That's really cool that y'all are thinking about this. And that actually sounds like a pretty decent experiment to try. We do a similar demonstration in our dry ice lab, where, I had this container right here. We'll get it back out. Our Erlenmeyer, or our graduated cylinder. You saw all that gas coming out. We would actually attach a nitrile glove, like a doctor's glove. We'd put it over the top and it would start inflating. So if you had a water balloon with hot water in it, and then you added a piece of dry ice, if you could add the dry ice without the water all squirting out, it would cause that balloon to start inflating, because the warm water would cause the dry ice to sublimate, and it would cause the balloon to expand. So that's a really cool way of thinking about it. And that's similar to like some of the demonstrations we've been doing here, but we certainly didn't do that. That's awesome that you can conceptualize how that might work.
Yeah, depending upon the size of your piece of dry ice to your size of your balloon, the balloon would eventually pop.
Thank you guys so much for answering our questions. We really enjoyed it.
Yay. Well,
All
thank
right.
you so much for asking your questions. We really enjoy answering them. We thank you very much for coming today, and we will see you guys later. All right.
All right. Good to see you.